Hello and welcome to the Crazy Hat Chemist, your source for all of your chemistry explanations. Today's video is not a lecture, but a paper and pencil explanation of a problem set in chemical reactions. You can see the worksheet right here. It's chemical reactions worksheet number 2. Before beginning this problem set, I will make the assumption that you have watched my playlist in Honors Chemistry number 7, the Chemical Nomenclature Collection. In addition, I will assume that you, 1, know the periodic trends of ions and charges. Number 2, know the polyatomic ions and charges. Number 3, know the nomenclature of binary covalent compounds. Number 4, know the nomenclature of ionic compounds. And number 5, know the nomenclature of acids. The second playlist I will assume you have watched is Honors Chemistry 8, the Chemical Reactions Collection. From that video series, I will assume you have number 1, you know the 5 basic types of chemical reactions. Number 2, you know the solubility rules, and you know the activity series. So without further ado, let's begin with chemical reactions worksheet number 2. A worksheet of which I have designed for understanding and comprehension of this unit in chemical reactions. So let's see what we can do here. All right, so the first thing here is we're going to read the question, and I'll just slide this up just a little bit here, and there we go. It says, number 1, in a closed container, 2 elements are mixed together, nitrogen and hydrogen. So what we're first going to do for every single one of these reactions is we're going to first write down the reactants. One of the things that you can also do is that you can look at the words of which are given here, and I have nitrogen and I have hydrogen. And they're mixed together, so that means that there's plus sign in between the two of them. Pretty much all the rest of these words really don't matter, so we can, scratch all that other garbage junk out of the way. Now what we need to do is we need to know our periodic trends and what the formula is of each of these elements. So the element nitrogen is N2 because it's one of the diatomics. Nitrogen is a diatomic and it is a gas at standard conditions. So the state of matter here is G for gas. The second element is hydrogen, and there's a plus sign in between these two. So hydrogen is also one of the diatomics. There are 7 diatomics, so we're going to write H2. Diatomic meaning 2 for atom, 2 atom molecule diatomic. Hydrogen is also a gas at standard conditions. Now from this, it says that the next thing that we need to do is draw an arrow. And then from this, we also need to figure out what type of reaction this is. And as we go through this, we're going to figure out what the different types of reactions these are. Okay, and this one, I have 2 reactants. I don't have any other information, and this is actually going to be a combination reaction. Okay, so a combination reaction, I'm going to put these 2 elements together. So what I'm going to look for here is how to combine these 2 elements. So from a periodic table, you should understand the charge on the hydrogen ion. And since it is in group 1, it would be a 1+ charge. And the nitride ion, and that would be there as a 3- charge. So what we're actually going to do is combine the nitrogen and the hydrogen together in their correct charge ratio. And I'll do this kind of up off to the side here. Hydrogen 1+ nitride, and that's a 3-. So we're going to take the bull by the horns, their absolute value of these 2 numbers, absolute value, bull by the horns, flip, bring it down. Effectively, what that means is this 1 comes here, this 3 comes here. Now, the other thing that we are going to do is we're going to write it in its standard form that you might be more familiar with. So right now, that standard form would be actually H3N that you're not familiar with because that's the cation first, then the anion. So you can actually write that as the product, and that would be perfectly fine. But for most of us in the chemistry world, we're going to write this as nitrogen and then the hydrogens, and then we're going to put 3. And then we should actually also be able to recognize what this compound is. And this is called ammonia. And ammonia under standard conditions is a gas. All right, fantastic. So that's our first step. This is an unbalanced equation. Again, this is a combination reaction, and I'm combining the two elements in their charge ratio. All right, now the next thing that we need to do is balance this reaction. And there is a variety of different ways of balancing, but I'm just going to point out one in particular for this one. We're going to balance the diatomics at the end, and we actually have 2 diatomics to balance. So that would be an interesting one. So then we're going to look at the hydrogens. So I have 2 hydrogens here, 3 hydrogens here, and I'm going to look for the greatest common factor between 3 and 2, and that would be 6. So I'm going to place a 2 right here in front of the ammonia, and then a 3 right here in front of the molecular hydrogen. And that would give me 6 hydrogens, and 2 times 3, that would be 6 hydrogens. There's 2 nitrogens and 2 nitrogens. Oh my gosh, perfect. That's balance. That's for our first combination reaction. All right, fantastic. Now what we're going to do is the next one. So I'm going to move this up just a little bit so you can see the next problem right there. This next one says decane is poured into a glass petri dish and burned with a lit match. All right, so first I'm going to write the formula for decane. That's C10H22. All right, and it says it's poured. And if you don't know already, decane being poured, that would be a liquid. So I'm going to write that state of matter. All right, so that poured indicates a liquid into a glass petri dish. Who cares about that? But this is a key word here, and that is burned. And so that burned is letting us know that this is a combustion type of reaction. So being that this is a combustion type of reaction, the other reactant that is necessary is molecular oxygen, and that is O2. That is also one of the diatomics. Molecular oxygen is a gas at standard conditions. And then we're going to do an arrow. And then what we're going to do above the arrow, we're going to put a delta sign. So every single combustion reaction requires a delta sign above the arrow. And the reason for that is that decane just doesn't combust or burn on its own. It needs a kick, and that kick could be a match or a Bunsen burner or an explosion, or you ignite it, something. The beautiful thing about every single combustion reaction is that the products are always the same. So, and that is going to be carbon dioxide, that is a gas, and water, that's H2O. And for this purpose here, we're going to write this as a liquid. Now, we really don't know if this is going to be a liquid or if it's going to be a gas for the water, but at this moment in time, we're just going to go with it being a liquid, okay? It depends on how exothermic this reaction is, whether it's a liquid or a gas. But for the most part, I'm going to follow along and say that water is going to be a liquid in these combustion reactions on the product side. Okay, perfect. Now, the next thing that we're going to do is we are going to balance combustion reactions in a particular order. And that particular order is we are going to first balance the carbons, then the hydrogens, then the oxygens in that order that's chosen. So how many carbons on the reactant side? That's 10. So I'm going to place a 10 right here in front of the carbon dioxide because there was 1 before. How many hydrogens on the reactant side? That's 22. So over here, I have 2, and I'm going to place an 11 right here, and then that will give me 22 hydrogens. So I'm going to look over here in this compound right here of the decane. Do I have any oxygens? The answer is no. So that's really critical to our understanding here. That means all the oxygens are right here in the O2. So what I'm going to do is I'm going to count up the number of oxygens with this coefficient of 10. So 10 times 2 would be 20 oxygens. Then including this coefficient of 11 with the water, 11 times 1, that is going to be 11 oxygen. So I'm going to add these two numbers up. That's going to equal 31. So there's a total number of 31 oxygens on the product side. Okay. And on the reactant side, I also need there to be 31 oxygens. So the next part that I'm going to do is, since I don't have any oxygens here, and 31 is an odd number, I'm going to do 31 divided by 2. So actually, this reaction is actually balanced with that coefficient of 31/2. But one of our rules here in this chemistry world at this level is that we cannot have fractional coefficients. So in order to get rid of that fractional coefficient, I'm going to multiply the entire equation by the denominator, which is a 2. So my ending stoichiometric coefficients is going to be a 2 for the decane, 31 for the molecular oxygen, 20 for the carbon dioxide, and 22 for the water. Again, the very last step, what you should be doing is actually double checking your work to make sure that it is balanced, but I will let you do that on your own. All right. Fantastic so far, I hope. All right, next one, number 3, says aqueous ferric dichromate. So ferric is iron that's a 3+ charge. Dichromate is Cr2O7, that's a 2- charge. And it says aqueous, so that means that it's aqueous. Is poured into an Erlenmeyer flask. Really, we don't matter about that, we don't care. And then it says ammonium oxide. Ammonium ion, and oxide is a periodic trend charge, and that's where we're going to go back to our periodic table. There's oxygen, oxide is a 2- charge right there like that. Okay, and so that's an O2 minus. So what we're going to do is we're going to take the bull by the horns, absolute value of these two numbers, flip them, bring them down, and we're going to come up with our two formulas for our reactant side. So that's going to be Fe 2 parentheses Cr2O7 parentheses and a 3. And it did say that it is aqueous, so that's why we're going to write AQ right here. Then for the, so that's ferric dichromate. That's what that is right there. Then the next one is ammonium oxide, and we're going to have NH4 parentheses and a 2 and an O. We're doing the same thing. Take the bull by the horn, flip, bring it down, absolute value. Then we're going to have this arrow here, and that will differentiate the reactants from the products. So what type of reaction is this? This is a double displacement reaction. And the characteristics of a double displacement reaction is that I have a cation and an anion, and a cation and an anion. That is the iron, the ferric is the cation, the dichromate is the anion, the ammonium ion is the cation, and the oxide is the anion. So what we're going to do is do a double displacement, which is a switch. So we're going to, on the product side, we're going to combine the ferric with the oxide, and then we're going to combine the ammonium ion with the dichromate right there like that. Okay, and so it doesn't matter which one you write first. It really doesn't matter. I'm just going to write the ferric oxide first, and we do take the absolute values of the charges, flip them, bring them down to get what the formula is for ferric oxide, and that's going to be Fe2O3. Okay. And we're going to come up with what this is in that parentheses in just a moment. And then we are also going to get our second product. Okay, I'm going to zoom on out here just a little bit because I think we need just a little bit more space. Here we go. Perfect. And now we're going to do ammonium dichromate. Okay, so ammonium dichromate is going to be, the ammonium ion is written first because that's the cation. There's a parentheses, a 2, and then we're going to write dichromate, Cr2O7. Okay, and yes, you can see all that now. Perfect. We're going to look at our solubility rules to come up with the states of matter that go inside these parentheses. Anything with ammonium ion is aqueous, period. And oxides. So oxides are insoluble except for ammonium oxide or the alkaline metals. The alkaline metals are the group 1 on your periodic table, absent of hydrogen, are the alkaline metals. So because iron 3+, that's ferric, is not an alkali metal, that means that this is a solid. This is a precipitation reaction. All right. Now what we're going to do is balance this. And so our very first step in balancing is that we are looking for the most complex formula with the most unique number of elements that you can find. The most complex formula here is this first one, the ferric dichromate. So we're going to base everything on this one. We're going to start here. So how many chromiums do I have? I have 6. Okay, so that's going to be important in our balancing here. So we're going to place a 3 right here in front of the ammonium dichromate, and that will give us 6 chromiums. Okay, then that you should see that that gives us actually 6 nitrogens. And right over here, we need to have 6 nitrogens, and we're going to place a 3 coefficient in front of the ammonium oxide. Now, your very last step is to count up the number of each element on both sides and make sure that they do equal. But I'm going to let you do that on your own. That's something for you to do. Okay, so I'm going to let you do that. And that's for some, like I said, something for you to do. So you're going to take care of it. But I guarantee you that that reaction is now balanced. Okay, all right. So next one, we're going to scroll this down right over here. And then we're going to do the next one. So the next one is ethane, okay, and that is C2H6. It says that it escapes from a gas cylinder. Oh my gosh, it's a gas cylinder. So that's letting us know that it's a gas, and it is ignited with a spark. So that also means that this reaction here is a combustion reaction. So I'm going to say plus O2, that's a gas, an arrow with a delta above it, because that is necessary. And the products are always for a combustion reaction. These are assumed to be complete combustion reactions. Carbon dioxide, that's a gas, and water, that's H2O, and that's going to be a liquid. As I said previously, as far as the state of matter for water being a liquid and not a gas. All right. So again, we're going to balance this combustion reaction in the same order that we balanced the other one. That's carbons, hydrogens, then oxygens. There are 2 carbons here. I'm going to place a 2 right here in front of the carbon dioxide. There are 6 hydrogens here on this side, and there are 2. So I'm going to place a 3 here. That will give me 6. I'm going to look at how many oxygens here, and that's 2 times 2, that's 4. I'm going to look at how many oxygens here. That's 3 times 1, that's 3. I'm going to add these up. That equals 7. So how many oxygens are on the product side right now? A total of 7. The carbons are balanced. The hydrogens are balanced. Now I need to balance the oxygens. So I have 7 oxygens on the product side, and that's an odd number. So I'm going to use a fractional coefficient. The denominator is always a 2. And then I'm going to have the numerator, the odd number, up there as a 7. And as I said, like on problem number 2, this reaction here, I'm going to have to multiply everything by a 2. So my ending coefficients will be a 2. This will turn into a 7 for the oxygen. This will be a 4, and this will be a 6. And what I didn't go over in detail on the previous number 3 problem, or even on the other ones, is that you're supposed to count up the number of each element on both sides to validate and verify that you have the correct number on both sides. And so we'll do that here. 2 times 2, that's 4 carbons on the reactant side. 4 times 1, that's 4 carbons on the product side. So the number of carbons are balanced. 2 times 6, that's 12 hydrogens on the reactant side. 6 times 2, that's 12 hydrogens. So they're balanced. Now the oxygens is 7 times 2, that's 14. And then 4 times 2, that's 8, plus 6, that's a total of 14. So I did validate that that is balanced. So we're actually rocking and rolling. We're good to go. Okay. Now let's do number 5. Okay. Number 5. Here we got number 5, and it says that we have a test tube of sodium oxalate. Okay, so who cares if it's test tube? Is added to a beaker of phosphoric acid. So I'm crossing out words that really don't matter for us. Okay, moving this up just a little bit here so we can go on to this next problem here. Perfect. Okay, and so sodium oxalate, again, what we're using is our periodic trends. Sodium is a group 1, it's a +1. and that's Na1 plus. Oxalate is C2O4 with a 2 minus. So that means that this is going to be a 2 here, C2O4. Anything with sodium in it is aqueous. So I'll write that right there. Plus phosphoric acid. Phosphoric is coming from the phosphate ion, that is PO4 3 minus, and I'm going to attach the appropriate number of hydrogens to that. So it'll be H3PO4, and that's aqueous because that's an acid. All right, the type of reaction of which this is it's a double displacement reaction. So I'm going to go with how I came up with the reactants to come up with the products. And I'm just going to write this right here so that you can see this. So I just did that in my head. Okay. And so our products are going to combine this sodium with this phosphate and this hydrogen with this oxalate. Okay. And it doesn't matter which one you write first, but the characteristic of this is that I have a cation anion and a cation anion. Hopefully that's good. So the sodium is going to get together with the phosphate, and I'm going to have Na3PO4. Anything with sodium in it is aqueous. All right. And then my next compound is going to be the H with the oxalate, and that's going to be H2C2O4, and that's also aqueous. Okay. All right. Fantastic. This is oxalic acid. This is sodium phosphate. And now what we need to do is balance this thing here. So again, you need to start off with the most complicated formula. That's probably the easiest thing to do. And that works out. It doesn't matter where you start off on this one. So we have 3 sodiums here, 2 sodiums here, greatest common factor of like what we did before. This is going to be a 2. This is going to be a 3. All right, I like that. 2 phosphorus, 1 phosphorus. So this will be a 2. Okay. And then I have 6 carbons over here and I have 2. So I'm going to have to put a 3 right there. And that will give me 6 carbons. And then again, your very last step is to verify and validate every single element to make sure that it is balanced. But I'm going to let you do that on your own. So that's up to you. All right, we're going to move this forward here and we're going to keep on moving this down. So our next one is powdered zinc oxide. So this word powdered does mean that it is a solid. It's heated in an oven without any air present. So heated, that's going to be a delta in an oven without any air. So this is an absence of anything else. So that means that this is a decomposition reaction. So zinc oxide, zinc is a 2+ charge. That's a periodic trend. And hopefully you know this. So in this diagonal pattern and like a reverse lambda, this is a 1+ for silver, a 2+ for zinc, a 3+ for aluminum, and a 2+ for cadmium. All right. So that's why I got the zinc as a 2+. And it said oxide, and we had already covered an oxide earlier, so we'll just pop that in there. We're going to take the absolute value of these 2 charges, flip the numbers, and write that as ZnO, and because we reduce that. It says that it's powdered, so that means that this is a solid. This is a decomposition, excuse me, it's a decomposition reaction, so I only have 1 reactant. It's the easiest ones to identify, and I'm going to have a delta above that right there. Now, in a decomposition reaction, what we typically want to get is we want to try to get a California and a gas, or we want to get an element and a gas. And that is going to be the particular case in this one. And the reason for that is that zinc only has a single charge. It's a periodic trend. So our element that we're going to get is just zinc, and that is going to be an element by itself. And so zinc is a solid. And the gas of which we are going to get is oxygen gas. Oxygen is a diatomic molecular gas, just like that. And now what we need to do is balance this. And so we have 1 zinc, 1 zinc. We have 2 oxygens on the product side, 1 oxygen on the reactant side, and then we're going to put a 2 right there. That unbalanced the zincs that we had, but we're going to put that 2 in front of that zinc. And we're ready to rock and roll, and that's good. One of the things is that is completely balanced. Make sure that you don't put a 2 right here. Okay, that doesn't work like that. Okay, you cannot change formulas once you have formulas. All right. Cool. We're going to work on the next one here. It says an Erlenmeyer flask containing, who cares about all that? It says fluorine is added to a volumetric flask of 25 mils. Who cares about that? Potassium bromide. Okay, so fluorine. Fluorine is right over here on our periodic table here. I'll show you that. Here it is right here. So I'm just going to mention this because I didn't mention it earlier, but here are the diatomics. What are the diatomics? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and one other, and that is hydrogen. So that means it's H2, N2, O2, F2, Cl2, Br2, I2. Okay, these are the only 7 elements which are diatomics in their standard state. That's 25 degrees Celsius and 1 atmosphere. So fluorine is one of those diatomics. So that's going to be F2, and it is a gas at room temperature pressure. Okay, and then we're going to have potassium bromide. Potassium is a group 1. Bromide is a halogen. That's a 1- charge. I'm going to take the absolute value of these two numbers, flip and bring them down, and I'm going to have KBr. Solubility rule says that all potassiums are aqueous, so this is aqueous. We have an arrow. This is characteristic of what's called a single displacement reaction or single replacement reaction. Okay, this is an element and a California, and we're going to have that same pattern on the product side of an element and a California. Okay, the fluorine is a nonmetal, so it's going to displace the nonmetal. Bromine is a diatomic, just like we discussed just a moment ago. So that's why it's Br2. Bromine is a liquid at standard conditions. And then we're going to have the fluoride ion, which is that, combined with the potassium ion for our other product. Remember, cations come first, anions come second. So that's going to be KF. Anything with potassium in it is going to be aqueous, so that's AQ. All right, now we have our unbalanced equation. Now we need to balance it. You can start here with 2 fluorines. There's 1 fluorine. I'm going to put a 2 in front of the potassium fluoride, and then 2 potassiums and 1 potassium. I'm going to put a 2 in front of the potassium bromide. Sweet and awesome. Okay, so that's actually 7 of them. We have 3 more to do of this type. So I'm going to switch over to the next piece of paper and the page here, and that comes right over here. And let's move this down to number 8. Okay, so here we go, number 8. Number 8, it says aluminum pieces. Pieces means that it's hopefully a solid. Is slowly added to iodine. So it doesn't matter if it's slowly or quickly added, that doesn't matter. So I've got aluminum. Aluminum is Al, and it is a solid at standard conditions. And then iodine. Iodine, so I'm going to go back to my periodic table here again, of which we had before, and right over here you should see that iodine, when it's by itself in its standard conditions, is a diatomic. So I'm going to have I2, and that is a solid. Okay, so aluminum is a solid because that's its standard state, right? So this is going to be an element and an element. This is a combination reaction. So I'm going to look on my periodic table and find out what the periodic trend charge for aluminum is. So again, silver 1+, zinc and cadmium 2+, aluminum 3+. And so that's why I'm going to get the 3+ for the aluminum. And the iodine is a 1- in this column right here with all the halogens. Okay, so the aluminum is a 3+, the iodine is a 1-. So I'm going to get the formula on the product side of Ali3. And this does not follow solubility rules, but if you take a solid and you combine them together, then you certainly have something that weighs more, that's heavier, and we'll call it a solid. There's more information to that, but that will give us, just for right now, the basics of it. We're going to start off with the most complicated formula, which is aluminum iodide right here. And you should notice something, that there's 1 aluminum on the reactant side, 1 on the product side. But what's unbalanced is are the iodines. So again, I'm going to use something that we used before, and that is 3 and 2. The greatest common factor is 6. And so I'm going to put a 2 here and a 3 here. That will give me 6 iodines on both the reactant, 3 times 2, or 2 times 3 on the product side. 2 aluminums. 2 aluminums, fantastic, we got that one balanced. Hopefully that's good for you. All right, we're going to move this up here and we're going to go for number 9. Okay, number 9, it says calcium shavings. So there's our element. Shavings is letting us know that it is a solid. Are placed in a beaker containing hydrofluoric acid. Okay, so calcium, it's a solid because it's an element in its standard state. And then it says hydrofluoric. So I'm assuming that you have watched my videos on nomenclature and acids. So this is a binary non-metal acid because it has the prefix of hydro and the ic acid. So it's hydro, root word ic acid. So the charge on a fluoride ion is 1 minus. 1 minus. The charge on a hydrogen, which is necessary for all acids, is a 1 plus. So I'm going to put these two together and I'm going to get HF, and that's aqueous, just like that. Okay, hopefully that works well for you. We're going to draw an arrow. We're going to ask ourselves what type of reaction this is. This is a single displacement reaction. So what's going to happen is this metal forms cations. This metal that forms cations is going to displace it. There's no metal to displace, but there is a cation to displace. Okay, and so what we're going to have is the hydrogen be the element all by itself. And like we discussed earlier with the diatomics, what are the diatomics? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. These, that's 7 right there. And oh, yes, hydrogen. There's the hydrogen, right? Okay, so that means that that's diatomic and that's a gas at standard conditions. Then I'm going to combine calcium and fluoride together. So calcium is a group 2, so that's why it's a +2. Fluoride is still the -1 charge of which it had before. So we're going to have calcium fluoride just like that. And that's going to be a 2 right there. Okay, everybody okay with that? Hopefully you're going to follow your solubility rules, and fluorides are soluble for the most part, except a few exceptions to that, of which, fluorides are soluble except a few exceptions, and that's magnesium, calcium, strontium, barium, and lead. So this is actually a solid that's formed right there like that. All right. So now what we need to do is balance this problem here. So we've got 2 fluorines right over here. 1, I'm going to put a 2 right there in the front. That gives us 2 hydrogens. There are 2 hydrogens, 1 calcium, 1 calcium. Bam! I'm done with that one. That's balanced. All right, let's move this up a little bit more. Go to our next problem. It says sodium hypochlorite, and this is what you put in swimming pools, actually, is heated vigorously in an evacuated oven. So sodium is a group 1. Hypochlorite is a polyatomic ion, ClO with a 1- charge. So I'm going to have NaClO. Okay, and this is going to be a solid, and this is going to be an arrow because there is no other reactant, because it says that it's heated in an evacuated oven. That evacuated oven lets us know that there is no other reactant. Okay, so like what we were trying to do before with the, this is a decomposition reaction. They are the easiest to identify in that it only has 1 reactant. Okay. And what we're trying to do here is come up with a California. That's a cation anion combination and a gas. Okay, so let's first start off with the gas, and we're going to find the gas. The gas is O, and so that's going to be oxygen. Why is it diatomic? Because it's an element all by itself. That's diatomic. And then I need to get a California. So I have not used the sodium or the chlorine. And sodium has a 1+ charge based on its periodic trend. Chloride ion has a 1- charge. So the correct formula is going to be NaCl. Okay, there's a plus sign in between these here. And sodium chloride, there is no, notice that this, I am not going to be following solubility rules on a decomposition reaction because there's no water in here. So solubility rules only work when you have things in water. So this is going to be a solid like this. Perfect. All right, now the next thing we need to do is balance this thing. And we start off with the most complicated thing, one sodium, one chlorine, the chlorines and the sodiums are balanced. The oxygen's 1, oxygen's 2. I'm going to put a 2 in front of the sodium hypochlorite. Consequently, I'm going to have to put 2 in front of the sodium chloride, and boom, now it's balanced. Perfect. All right, problem number 11, and the last problem on this particular review worksheet. Here we go. So this one is a different type of reaction entirely, and this is called a net ionic equation that we're trying to write. And for the purposes of what we are doing here, the net ionic equations are always going to follow a double displacement reaction, noting that that is not the case in real life, okay? But for right now, we're going to follow this double displacement reaction as a for our net ionic equations, okay? So we're going to get stannic nitrate is mixed with potassium hydroxide in a beaker. Who cares if you observe it or not? Stannic is tin, that's SN, that's a 4+. Nitrate is NO3 with a 1-. Potassium, that's a polyatomic ion. Potassium is a group 1+ charge. Hydroxide is a 1- charge. That's also a polyatomic ion. So I'm going to combine these two things to come up with my reactant, and I'm going to combine these two things to come up with my product. Okay. Sorry, these two with my reactant, these two with my reactant, and then I'm going to combine the stannic with the hydroxide for one of my products, and the potassium and the nitrate for the other product. So this is something that I went over in my lecture. So again, I highly recommend that you follow my videos and first watch the lecture on chemical reactions. And what I'm going to do is we're going to do a shortcut. Okay, we are going to find which product, either the blue circles or the red squares, is going to be the precipitate. So we're looking at solubility rules. So hydroxides are insoluble except for ammonium ion, no. Alkali metals, no. And then let's just double check. So potassiums are aqueous. Nitrates are aqueous. You only have to check one of these. So potassium nitrate is not the product. So what I'm going to write is stannic hydroxide as my product. That's SN parentheses OH and a 4. That's a solid because it's following solubility rules. And what we're going to do here is we're going to take this and effectively go in reverse and do kind of like a decomposition, but in reverse. It's kind of like a decomposed taco, if you've ever had one of those for a meal of some kind. But you take on your plate, you get your taco, but in little tiny pieces. That is, you just get an empty shell, some rice, maybe some beans, maybe some hot sauce and guacamole and stuff like that. And then you have to make it yourself. So this is a decomposition, if you will, by going backwards. Again, it is a double displacement reaction, but we're doing a net ionic equation and we're decomposing this product to come up with the two reactants, of which are always going to be aqueous. So the tin is a 4+, that's SN 4+. This is always aqueous on the reactant side. And then hydroxide, that's an OH with a 1-. That's also aqueous. Cool. Now, the next thing that we need to do is we need to make sure that this is balanced. There's 1 tin, 1 tin, there's 4 hydroxides, and there's 1. So I need to place a 4 right here. And then I have my net ionic equation. I hope that was worth your time watching that video. And please subscribe to my YouTube channel, The Crazy Hat Chemist, and watch for more of these videos. So have a good day and a good evening. Talk to you later. Bye now.